Hello, my name is Jay Ocampo. Welcome to Module 1, Lesson 6 of our Cisco and Core video series about quality of service. In this lesson, we will first talk about an introduction to quality of service and what it is. We will also cover the QoS model and QoS Toolset Overview. We're also going to be discussing about the classification and marking, how congestion management work, what is congestion avoidance, what is traffic policing and shaping, and what are the link-specific tools. The networks today will have a mix of data, voice, and video, and each of this kind of traffic has very unique properties. For example, data traffic is not real-time traffic. It's comprised of bursty or unpredictable and widely varying packet arrival times. Many types of data applications, such as email, are relatively non-interactive and therefore are not delay sensitive. This, however, voice and video traffic is different. Voice and video traffic is real-time traffic and requires constant and predictable packet arrival times. This type of traffic is very drop and delay sensitive, and therefore it requires special treatment from the network. Modern real-time multimedia applications such as IP telephony, telepresence, broadcast video, Cisco WebEx, and IP video surveillance are extremely sensitive to delivery delays and create unique quality of service demands on the network. When packets are delivered using a best effort delivery model, they may not arrive in order or in a timely manner, and they may be dropped. For video, this can result in pixelization of the image, pausing, choppy video, audio and video out of sync, or no video at all. For audio, it could cause echo, talker overlap, unintelligible and distorted speech, voice breakups, long silence gaps, and call drops. The following are the leading causes of quality issues. The first one is lack of bandwidth. The available bandwidth on the data path from a source to a destination equals the capacity of the lowest bandwidth link. When the maximum capacity of the lowest bandwidth link is surpassed, link congestion takes place, resulting in traffic drops. The obvious solution to this type of problem is to increase the link bandwidth capacity. But this is not always possible due to budgetary or technological constraints. Another option is to implement QoS mechanisms such as policing and queuing to prioritize traffic according to the level of importance. Voice, video, and business-critical traffic should get prioritized forwarding and sufficient bandwidth to support their application requirements, and the least important traffic should be allocated with the remaining bandwidth. The second one is latency and jitter. One-way end-to-end delay, also referred to as network latency, is the time it takes for packets to travel across a network from a source to a destination. The ITU recommendation for G114 recommends that, regardless of the application type, a network latency of 400 milliseconds should not be exceeded. And for real-time traffic, network latency should be less than 150 milliseconds. However, ITU and Cisco have demonstrated that real-time traffic quality does not begin to significantly degrade until network latency exceeds 200 milliseconds. To be able to implement this recommendation, it is important to understand what causes network latency. So the types of latency are the propagation delay, serialization delay, processing delay, and all of these are fixed delays. And the other one is the delay variation, which is a variable type of delay. The third contributor is the packet loss. Packet loss is usually a result of congestion on an interface. Packet loss can be prevented by implementing one of the following approaches. The first one is increased link speed. You can also implement QoS congestion avoidance and congestion management system. You can implement traffic policing to drop low priority packets and allow high priority traffic through. You can implement traffic shaping to delay packets instead of dropping them, since traffic may burst and exceed the capacity of an interface buffer. Traffic shaping is not recommended for real-time traffic because it relies on queuing that can cause jitter. There are three basic steps involved in implementing QoS on a network. Step 1 is to identify the traffic and its requirement. You have to study the network to determine the type of traffic running on the network and then determine the QoS requirements for the different types of traffic. Step number 2 is to group the traffic into classes with similar QoS requirements. In the example, 3 classes of traffic might be defined. It could be voice, video, and mission critical data or best effort data. Step number 3 is to define the QoS policies that will need the QoS requirements for each traffic class. The first step in implementing QoS is identifying the traffic on the network and determining QoS requirements and the importance of the various types of traffic. This step consists of these activities. Number 1, determine the QoS problems of users. On this step, you have to measure the traffic on the network during congested periods. You can conduct CPU utilization assessment on each of the network devices during busy periods to determine where problems might be occurring. The next step is to determine the business model and goals and obtain a list of business requirements. This activity helps define the number of classes and allows you to determine the business requirements for each traffic class. The third step is to define the service levels required by different traffic classes in terms of response time and availability. If we speak about service levels, here are a few questions to ask. What is the impact on business if a transaction is delayed by 2 or 3 seconds? Can file transfers wait until the network is underutilized? A typical enterprise might define 5 traffic classes. The first one is voice, which is the absolute priority, right? Which is the VoIP traffic. Second one is video, which is tagged as the second priority after voice. The next one is mission critical. So with mission critical traffic, these are small sets of locally defined critical business applications. After mission critical, it should be the transactional type of class. It talks about the database access. It could be transactional services, interactive traffic, and preferred data services. After transactional, it could be the best effort type of traffic. Email is an example of a best effort type of traffic. And the lowest class is scavenger. So scavenger traffic are the unspecified traffic and is considered as less priority than the best efforts. Scavenger applications such as BitTorrent and other point-to-point applications will be served by that class. Now let's talk about how a sample QoS policy looks like. So it's going to be divided into different priority and it's going to be mapped to different traffic types. If we speak about the highest priority, which is priority number 5, it's going to be voice and video. So voice and video should at least have a minimum bandwidth of 1 Mbps and should use what we call as LLQ or low latency queuing to always give voice the priority. The second priority is mission critical data, which is being tagged on a priority number 4. The minimum bandwidth for mission critical data should at least be 1 Mbps and should use class-based weighted for queuing or CBWFQ to prioritize critical class traffic flows. The third priority is transactional data, which is tagged as priority number 3. The minimum bandwidth for transactional data is also 1 Mbps and must use class-based weighted for queuing to prioritize transactional data traffic flows. The next priority, which is a best effort, is tagged as a priority 2. It should have a maximum bandwidth of 500 kbps and it should use CBWFQ to prioritize best effort traffic flows that are below mission critical and transactional data. And the lowest priority is scavenger. It should at least have a maximum bandwidth of 100 kbps and it will use a WRED or weighted random early detection to drop these packets whenever the network has a tendency towards congestion. There are 3 different QoS implementation models. The first one is best effort. In best effort, QoS is not enabled. It is used for traffic that does not require any special treatment. The second one is the integrated services. With integrated services, applications signals the network to make a bandwidth reservation and to indicate that they require special QoS treatment. And the third one is the differentiated services or DiffServ. On this model, the network identifies classes that require special QoS treatment. Let's expand the discussion further about the differences of each. So the first one again is the best effort model. So the internet was designed for best effort and no guarantee of delivery of packets. This behavior is still predominant on the internet today. If QoS policies are not implemented, traffic is forwarded using the best effort model. All network packets are treated exactly the same. An emergency voice message is treated exactly like a digital photograph attached to an email. Without QoS implemented, the network cannot tell the difference and as a result, cannot treat packets preferentially. When you drop a letter in a standard postal mail, you are using a best effort model. Your letter will be treated exactly the same as every other letter. With the best effort model, the letter may never arrive, and unless you have a separate notification arrangement with the letter recipient, you may never know that the letter did not receive. The best effort model has these significant benefits. The model has nearly unlimited scalability, and the only way to reach scalability limits is to reach bandwidth limits, in which case all traffic is equally affected. With the best effort model, you do not need to employ special QoS mechanisms to use the best effort model. It is the easiest and quickest model to deploy. Now, what are the drawbacks of the best effort model? On a best effort model, nothing is guaranteed. Packets will arrive whenever they can, in any order possible. If they arrive at all, packets are not given preferential treatment. Also, critical data is treated the same way as a casual email. Now let's talk about the IntServ model. Development of the IntServ architecture model was motivated by the needs of real-time applications, such as remote video, multimedia conferencing, visualization, and virtual reality. The model provides a way to deliver the end-to-end QoS that real-time applications require by explicitly managing network resources to provide QoS to specific user packet streams or flows. The IntServ model uses resource reservation and admission control mechanism as key building blocks to establish and maintain QoS. This practice is similar to a concept known as hard QoS. With hard QoS, traffic characteristics such as bandwidth, delay, and packet loss rates are guaranteed end-to-end. This guarantees ensures both predictable and guaranteed service levels for mission-critical application. IntServ uses Resource Reservation Protocol, or RSVP, to explicitly signal the QoS needs of the traffic of an application along the devices in the end-to-end path through the network. If network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. If the requested reservation fails along the path, the originating application will not send any data. IntServ requires several functions on routers and switches along the path. These functions include the following. Admission control. It determines whether a new flow requested by users or systems can be granted the requested QoS without affecting existing reservations in order to guarantee end-to-end QoS. Classification. It entails using a traffic descriptor to categorize a packet within a specific group to define that packet and make it accessible for QoS handling on the network. Classification is pivotal to policy techniques that selects packets traversing a network element or a particular interface for different types of QoS service. Policing. Policing, it takes action including possibly dropping packets when traffic does not conform to its specified characteristics. Policing is defined by rate and burst parameters, as well as by actions for in-profile and out-of-profile traffic. Queuing. Queuing is designed to accommodate temporary congestion on an interface of a network by storing excess packets in buffers until access to the bandwidth becomes available. And the last one is scheduling. Scheduling talks about the QoS scheduler and negotiates simultaneous requests for network access and determines which queue receives priority. Generally, queues are scheduled in a round-robin fashion. Now, let's talk about the benefits of IntServ. IntServ supports admission control that allows a network to reject or downgrade new RSVP sessions if one of the interfaces in the path has reached the limit. RSVP signals QoS request for individual flow. In the request, the authorized user and needed traffic policy are sent. The network can then provide guarantees to these individual flows. RSVP informs network devices of flow parameters like IP addresses and port numbers. Some applications use dynamic port numbers such as 8H.323 based applications, which can be difficult for network devices to recognize. NBAR, or Network-Based Application Recognition, is a mechanism that has been introduced to supplement RSVP for applications that use dynamic port numbers but do not use RSVP. What are the drawbacks of IntServ? IntServ has a continuous signaling because of the stateful RSVP architecture. The flow-based approach is not scalable to large implementations, such as the public internet, because RSVP has to track each individual flow. This circumstance would make end-to-end signaling very difficult. A possible solution is to combine IntServ with elements from the DiffServ model to provide the needed scalability. Now let's talk about the DiffServ model. DiffServ was designed to overcome the limitations of both the best effort and IntServ models. The DiffServ model is described in IETF RFC 2474 and 2475. DiffServ can provide an almost guaranteed QoS while still being cost-effective and scalable. The DiffServ model is similar to a concept known as soft QoS. With soft QoS, QoS mechanisms are used without prior signaling. In addition, QoS characteristics, like bandwidth and delay, are managed on a hop-by-hop basis by policies that are established independently at each intermediate device in the network. This action is also known as per-hop behavior or PHP. The soft QoS approach is not considered an end-to-end QoS strategy because end-to-end guarantees cannot be enforced. However, soft QoS is a more scalable approach to implementing QoS than hard QoS or the IntServ model because many of applications can be mapped into a small set of classes upon which similar sets of QoS behaviors are implemented. Although QoS mechanisms in this approach are enforced and applied on a hop-by-hop basis, uniformly applying global meaning to each traffic class provides both flexibility and scalability. With DiffServ, network traffic is divided into classes based on the business requirement. Each of the classes can then be assigned a different level of service. As the packets traverse a network, each of the network devices identifies the packet class and services the packet according to that class. It is possible to choose many levels of service with DiffServ. For example, voice traffic from IP phones is usually given preferential treatment over all the other application traffic, such as email. Email is generally given best effort service, and non-business traffic can either be given very poor service or blocked entirely. DiffServ works like a packet delivery service. You request and pay for a level of service when you send your package. Throughout the package network, the level of service is recognized and your package is given either preferential or normal service depending on what you requested. What are the key benefits of DiffServ? It is very highly scalable. It provides many different levels of quality. Now, what are the drawbacks of DiffServ? There's no absolute guarantee of service quality that can be made. And it also requires a set of complex mechanisms to work in concert throughout the network. Cisco provides a complete toolset of QoS features and solutions for addressing the diverse needs of voice, video, and multiple classes of data applications. Cisco QoS technology lets complex networks control and predictably service a variety of network applications and traffic types. You can effectively control bandwidth, delay, jitter, and packet loss with these mechanisms. By ensuring the desired results, the QoS features lead to efficient, predictable services for business-critical applications. Using the rich QoS toolset, businesses can build networks that conform to the differentiated services or DiffServ architecture. So these toolsets are the classification and marking tools, policing and markdown tools, scheduling tools, traffic shaping, and link-specific tools. The first element to a QoS policy is to classify or identify the traffic that is to be treated differently. Following classification, marking tools can set an attribute of a frame or packet to a specific value. Such marking establishes a trust boundary that scheduling tools later depend on. So what are these parameters? It can be layer 2 parameters about 802.1q cost bits or class of service bits, or it can be MPLS experimental values. What are the layered 3 parameters? It could be IPP or IP precedence. It could be DSCP or differentiated services code points. It can be the IP explicit congestion notification or ECN, or the source and destination IP addresses. What about the layer 4 parameters? This can be the layer 4 protocol like TCP and UDP, or source and destination ports. For the layer 7 parameters, we can talk about application signatures via NBAR or network-based application recognition. As you may know, NBAR is a Cisco proprietary technology that identifies application layer protocols by matching them against a PDLM or a protocol description language module, which is essentially an application signature. The NBAR DIP packet classification engine examines the data payload of stateless protocols against PDLMs. There are over 98 PDLMs embedded into the Cisco iOS software code. Additionally, Cisco iOS introduces the ability to define custom PDLMs, which examine user-defined strings within packet payloads. PDLMs can be added to the system without requiring an iOS upgrade. NBAR is dependent on Cisco Express Forwarding or CEF and performs DIP packet classification only on the first packet of a flow. The remainder of the packets belonging to the flow is then CEF switched. You can only apply policies to traffic after it had been positively classified. To avoid the need for repetitive and detailed classification at every node, packets can be marked according to their service levels. Here's an analogy. So imagine that each individual in the postal system would have to open up each letter to determine the respective priority required and service it accordingly. Obviously, it would be better to have a first mail clerk stamp something on the outside of the envelope to indicate the priority level that would be applied during each phase of the processing and delivery. Similarly, marking tools can be used to indicate respective priority levels by setting attributes in the frame or packet headers so that detailed classification does not have to be recursively performed at each hop. Within an enterprise, marking is done at either layer 2 or layer 3. Various layer 2 and layer 3 fields are used for marking traffic. QoS, TOS, DSCP, class selector, and TID are different terms to describe designated fields in a frame or packet header. How devices treat packets in your network depends on the field values. Ultimately, there are various Layer 2 and Layer 3 mechanisms that are used in the network for marking traffic. In addition to the mentioned marking fields, there are also numerous other technologies that allow marking. Such examples are GRE, MPLS, and IPsec. Layer 3 packet marking with IP precedence and DSCP is the most widely deployed marking option because Layer 3 packet markings have end-to-end significance. Layer 3 markings can also be easily translated to and from Layer 2 markings. Here are some additional important points. For IP routing, when addressing the QoS needs of IP routing traffic, the following guidelines are recommended. IP routing traffic should be marked to DSCP CS6. This is the default behavior on Cisco iOS platforms. Interior gateway protocols usually adequately are protected with the Cisco iOS internal pack priority mechanisms. Exterior gateway protocols such as BGP are recommended to have an explicit class for IP routing with a minimal bandwidth guarantee. Cisco iOS automatically marks IP routing traffic to DSCP CS6. When addressing the QoS needs for network management traffic, the following guidelines are recommended. Network management traffic should be marked to DSCP CS2. Then, network management applications should be protected explicitly with a minimal bandwidth guarantee. Now, let's talk about the trust boundaries. Trusting end users and their PCs is generally not recommended because newer operating systems like Windows and Linux makes it relatively easy to set QoS and DSCP markings on PC network interface cards. Improperly set QoS markings can affect the service levels of users within an enterprise. One of the main advantages of IP telephony is the simplicity and related cost savings of adding, moving, or changing a user. To move, a user simply picks up the IP phone, plugs it in at his or her new location, and carries on business as usual. If the infrastructure supports inline power, it is literally a matter of unplugging a single RJ45 cable and plugging it in at the new location. IP phones are trusted devices, while PCs are not. This can be a problem when provisioning trust in a mobile environment. For example, port A is configured to trust the endpoint connected to it, which initially is an IP phone. Then, port B is configured not to trust the endpoint connected to it, which initially is a PC. Because of a move, these endpoints get plugged into opposite ports. This change breaks the VoIP quality of calls made from the IP phone, which is now plugged into an untrusted port, which is B, and opens the network to unintentional or deliberate abuse of provisioned QoS by the PC, which is now on a trusted port in port A. Cisco switches with QoS intelligence use CDP or Cisco Discovery Protocol to discover whether any devices plugged into its ports can be trusted. If the device can be trusted, it is a Cisco IP phone. The switch extends trust to the device dynamically. If CDP determines that the device cannot be trusted, like it's a PC, the switch does not extend the trust boundary to the device. NBAR supports simpler configuration than modular QoS CLI or MQC configuration, where classifications and protocol-related details need to be manually configured. NBAR supports stateful recognition of flows. The simpler configuration means that a protocol analyzer capture does not need to be examined to calculate ports and details. Stateful recognition means smarter and deeper packet recognition. NBAR can be used to recognize packets belonging to different types of application. Static applications establish sessions to well-known TCP or UDP destination port numbers. Such applications like SMTP or Simple Mail Transfer Protocol could also be classified by using Access Control Lists or ACLs. Dynamic applications use multiple sessions that use dynamic TCP or UDP port numbers. Typically, there is a control session to a well-known port, and the other sessions are established to a destination port numbers negotiated through the control session, such as used in FTP. NBAR inspects the port number exchange through the control session. NBAR also has the capability to inspect some applications for other information and to classify based on that information. For example, NBAR can classify HTTP sessions based on the requested URL, including MIME type or hostname. Now let's talk about congestion in queuing. Congestion can occur anywhere within the network, where speed mismatches, aggregation, or confluence accrue. Congestion management features control the congestion when it occurs. One way that network elements handle an overflow of arriving traffic is to use a queuing algorithm to sort the traffic and then determine some method of prioritizing it into an output link. Each queuing algorithm was designed to solve a specific network traffic problem and has a particular effect on the network performance. Many algorithms have been designed to serve different needs. A well-designed queuing algorithm provides some bandwidth and delay guarantees to priority traffic. Speed mismatches are most common reason for congestion. It is possible to have persistent congestion when traffic is moving from a LAN to a WAN, such as when traffic moves from a high-speed LAN environment like 100 or 1000 Mbps to a lower speed WAN link like 1 or 2 Mbps. Speed mismatches are also common in LAN to LAN environments when, for example, a 1 gig link feeds into a 100 Mbps link, but in those cases, they are transient. Typical points of aggregation occur in WANs when multiple remote sites feed into a central site. In the LAN environment, congestion resulting from aggregation often occurs at the distribution layer of the network, where the access layer devices feed traffic to the distribution layer switch. During periods with low traffic loads, when no congestion occurs, packets are sent out the interface as soon as they arrive. During periods of transmit congestion at the outgoing interface, packets arrive faster than the interface can send them. When congestion management features are being used, packets accumulating at an interface are placed in software queues according to their assigned priority and the queuing mechanism configured for that interface. They are then scheduled for transmission when the hardware buffer of the interface is free to send them. The router determines the order of a packet transmission by controlling which packets are placed in each queue and how the queues are serviced with respect to each other. Now let's talk about queuing algorithms. Queuing is designed to accommodate temporary congestion on an interface of a network device by storing excess packets in buffers until bandwidth becomes available or until the queue depth is exhausted and packets have to be dropped. Queuing is a congestion management mechanism that allows you to control congestion by determining the order in which identified packets are sent out an interface based on priorities assigned to those packets. Congestion management entails creating queues, assigning packets to those queues based on the classification of the packet, and scheduling the packets in a queue for transmission. Cisco routers support several queuing methods to meet the varying bandwidth, jitter, and delay requirements of different applications. The default mechanism on most interfaces is the very simplistic FIFO queue. Some traffic types, such as voice and video, have very demanding delay and jitter requirements, so more sophisticated queuing mechanisms must be configured on interfaces used by voice and video traffic. Complex queuing generally happens on outbound interfaces only. A router queues packets being transmitted out an interface. Here are the key queuing algorithms. The first one is FIFO, or first in, first out. This is the simplest algorithm. The second one is a PQ, or priority queuing, and it allows traffic to be prioritized. The third algorithm is round robin, and it allows several queues to share bandwidth. And the last one is WRR, or weighted round robin, and it allows sharing of bandwidth with prioritization. So what is FIFO, or first in, first out? So FIFO is the simplest queuing algorithm. FIFO provides basic store and forward capability. It is the default queuing algorithm in some instances, thus requiring no configuration. In its simplest form, FIFO queuing, also known as first come first serve or FCFS queuing, involves storing packets when the network is congested and forwarding them in order of arrival when the network is no longer congested. FIFO embodies no concept of priority or classes of traffic and consequently makes no decision about the packet priority. There is only one queue and all packets are treated equally. Packets are placed into a single queue and transmitted in the order in which they arrive. Higher priority packets are not transmitted faster than lower priority packets. When FIFO is used, ill-behaved sources can consume all the bandwidth, and bursty sources can cause delays to time-sensitive or important traffic. Also, important traffic can be dropped because less important traffic has filled the queue already. When no other queuing strategies are configured, all interfaces except serial interface at E1 and below use FIFO by default. FIFO, which is the fastest method of queuing, is effective for large links that have little delay and minimal congestion. If your link has very little congestion, FIFO queuing may be the only queuing you need to use. All individual queues are, in fact, FIFO queues. Other queuing methods rely on FIFO as the underlying queuing mechanism for the discrete queues within the more complex queuing strategies that support advanced function such as prioritization. Next one is PQ, or priority queuing. Priority queuing allows you to define how traffic is prioritized in the network. You configure 4 traffic priorities. You can define a series of filters based on packet characteristics to cause the router to place traffic into these 4 queues. The queue with the highest priority is serviced first until it is empty. Then the lower queues are serviced in sequence. During transmission, PQ gives priority queues absolute preferential treatment over low priority queues. Important traffic, given the highest priority, will always take precedence over less important traffic. Packets are classified based on user-specified criteria and placed in one of the 4 output queues, 1, 2, 3, and 4, based on the assigned priority. Packets that are not classified by priority fall into the normal queue. A priority list is a set of rules that describe how packets should be assigned to priority queues. A priority list might also describe a default priority or the queue size limits of various priority queues. Packets can be classified by the following. Either it can be the protocol type, the incoming interface, the packet size, the fragments, or by using access control list or ACLs. Keep alives sourced by the network server are always assigned to the high priority queue. All other management traffic, such as EIGRP updates, must be configured. Priority queuing provides absolute preferential treatment to high priority traffic, ensuring that mission-critical traffic traversing various WAN links gets priority treatment. In addition, PQ provides a faster response time than do other methods of queuing. Although you can enable priority output queuing for any interface, it is best suited to low bandwidth congested serial interface. The next algorithm is round robin. A round robin is an arrangement of choosing all elements in the group equally in some rational order, usually starting from the top to the bottom of a list and then starting again at the top of the list and so on. A simple way to think of round robin is that it is about taking turns. In round-robin queuing, one packet is taken from each queue, and then the process repeats. If all packets are of the same size, all queues share the same bandwidth equally. If packets being put into one queue are larger, that queue will receive a larger share of bandwidth. No queue will starve with round-robin queuing because all queues receive a priority to dispatch a packet for every round. A limitation of round-robin queuing is the inability to prioritize traffic. And the fourth queuing algorithm is WRR, or weighted round-robin. In WRR, packets are accessed in a round-robin style, but queues can be given priorities called weights. For example, in a single round, 4 packets from a high priority class might be dispatched, followed by 2 from a middle priority class, and then 1 from a low priority class. Some implementations of the WRR algorithm dispatch a configurable number of bytes during each round. Some implementations of the WRR algorithm provide prioritization by dispatching a configurable number of bytes for each round rather than number of packets. The Cisco custom queuing mechanism is an example of this implementation. Router queuing components. Queuing on routers is necessary to accommodate burst when the arrival rate of packets is greater than the departure rate, usually because of one of two reasons. The input interface is faster than the output interface, or the output interface is receiving packets from multiple other interfaces. Initial implementations of queuing used a single FIFO strategy. More complex queuing mechanisms were introduced when special requirements required routers to differentiate among packets of different importance. Queuing was split into 2 parts. The first one is hardware queue. Hardware queue uses FIFO strategy, which is necessary for the interface drivers to transmit packets one by one. The hardware queue is sometimes referred to as the transmit queue. The second queue is the software queuing system. It schedules packets into the hardware queue based on the quality of service requirements. Weighted fair queuing, or WFQ. WFQ is one of the premier Cisco queuing techniques. It is a flow-based queuing algorithm that does 2 things simultaneously. It schedules interactive traffic to the front of the queue to reduce response time, and it fairly shares the remaining bandwidth among the various flows to prevent high-volume flows from monopolizing the outgoing interface. The idea of WFQ is to have a dedicated queue for each flow without starvation, delay, or jitter within the queue. Furthermore, WFQ allows fair and accurate bandwidth allocation among all flows with the minimum scheduling delay. WFQ makes use of the IP precedence bits as a weight when allocating bandwidth. WFQ was introduced as a solution to the problems of the following queuing mechanism. FIFO queuing causes starvation, delay, and jitter, while priority queuing can cause starvation of lower priority classes and suffers from the FIFO problems with each of the 4 queues that it uses for prioritizations. WFQ classification. A flow is identified based on the following information taken from the IP header and the TCP or UDP headers. This information refers to the source IP address. It can be the destination IP address, the protocol number identifying TCP or UDP, the type of service field or the TOS field, the source TCP or UDP port numbers, and the destination TCP or UDP port numbers. These parameters are usually fixed for a single flow, although there are some exceptions. For example, a quality of service design can mark packets with different IP precedence bit values even if they belong to the same flow. You should avoid such marking when using WFQ. The parameters are used as input for a hash algorithm that produces fixed length number that is used as the index of the queue. WFQ uses a fixed number of queues. The hash function is used to assign a queue to a flow. There are 8 additional queues for system packets and optionally up to 1,000 queues for RSVP flows. The number of dynamic queues that WFQ uses by default is based on the interface bandwidth. With the default interface bandwidth, WFQ uses 256 dynamic queues. The number of queues can be configured in the range between 16 to 4096. The WFQ mechanism provides simple configuration, or no manual classification is necessary, and it guarantees throughput to all flows. It drops packets off the most aggressive flows. Because WFQ is a standard queuing mechanism, it is supported on most platforms and in most Cisco versions. As good as WFQ, it does have its own drawbacks. WFQ have multiple flows and can end up in a single queue. WFQ does not allow a network engineer to manually configure the classification. Classification and scheduling are also determined by the WFQ algorithm. WFQ is supported only on links with a bandwidth less than or equal to Mbps. And lastly, WFQ cannot provide fixed guarantees to traffic flows. Neither the basic queuing methods nor the more advanced weighted fair queuing method completely solves the quality of service problems resulting from converged network traffic. The following problems remain. If only a priority queue is used for a voice-enabled network, voice gets the needed priority. However, data traffic would suffer. If only custom queuing is used for a voice-enabled network, data traffic is assured of some bandwidth. However, voice traffic would suffer delays. If WFQ is used, voice still experiences delay even when treated fairly by WFQ. In PQ and CQ, all of the classification, marking, and queuing mechanisms are complicated to use and time-consuming when applied on an interface-by-interface basis. Newer queuing mechanisms were developed to combine the best aspects of existing queuing methods. LLQ is a combination of CBWFQ, which assigns weights according to bandwidth, and a priority system based on class that gives voice the priority it requires while ensuring that the data is serviced efficiently. The potential starvation problem of the priority queue is solved by including a policing function based on the configured bandwidth of the priority system. Class-based weighted fair queuing extends the standard fair queuing functionality to provide support for user-defined traffic classes. With CBWFQ, you define traffic classes based on match criteria, including protocols, access control list, and input interfaces. Packets satisfying the match criteria for a class constitute the traffic for that class. A queue is reserved for each class, and traffic belonging to a class is directed to the queue for that class. Low latency queuing, or LLQ, extends the capabilities of CBWFQ with support for a single strict priority queue. Strict priority queuing gives delay-sensitive data, such as voice preferential treatment over all the other queued traffic. After a class has been defined, and its match criteria have been formulated, you can assign characteristics to the class. To characterize a class, you assign it with bandwidth and maximum packet limit. The bandwidth assigned to a class is the minimum bandwidth delivered to the class during congestion. To characterize a class, you also specify the queue limit for that class, which is the maximum number of packets allowed to accumulate in the class queue. The queuing guarantees the minimum bandwidth, but also gives a class unlimited access to more bandwidth if more is available. After a queue has reached its configured queue limit, and queuing of additional packets to the class causes tail drop or random packet drop, depending on how the class policy is configured. You can configure up to 64 discrete classes in a service policy. CBWFQ supports multiple class maps to classify traffic into its corresponding FIFO queues. Tail drop is used for CBWFQ classes unless you explicitly configure a policy for a class to use WRED or Weighted Random Early Detection to drop packets as a means of avoiding of congestion. Note that if you use the WRED packet drop instead of tail drop for one or more classes in a policy map, you must ensure that WRED is not configured for the interface to which you attach that service policy. Serial interfaces at E1 and below use WFQ by default. Other interfaces use FIFO by default. Enabling CBWFQ on a physical interface overrides the default interface queuing method. The CBWFQ mechanism calculates weights based on the available bandwidth. These weights are then used by the CBWFQ mechanism to dispatch the packets. You can configure bandwidth guarantees by using one of the following commands. The bandwidth command allocates a fixed amount of bandwidth by specifying the amount in kilobits per second. The reserved bandwidth is subtracted from the available bandwidth of the interface where the service policy is used. The allocated bandwidth will also be within the configured reservable limit, which is 75% of the interface bandwidth by default. The bandwidth percent command can be used to allocate a percentage of the total available bandwidth of an interface. The total interface bandwidth is defined by using the bandwidth interface command. It is recommended that the bandwidth command reflect the real speed of the link. The allocated bandwidth is subtracted from the available bandwidth of the interface where the service policy is used. The bandwidth remaining percent command is used to allocate the amount of guaranteed bandwidth based on the relative percentage of available bandwidth. When the bandwidth remaining percent command is configured, hard bandwidth guarantees may not be provided and only relative per class bandwidths are assured. That is, class bandwidths are always proportionate to the specified percentages of the interface bandwidth. When the link bandwidth is fixed, class bandwidth guarantees are in proportion to the configured percentages. If the link bandwidth is unknown or variable, class bandwidth guarantees in kilobits per second cannot be computed. A single service policy cannot mix the bandwidth, which is fixed in kilobits per second, and bandwidth percent commands except with strict priority queues. The weights needed for scheduling are calculated by CBWFQ process based on the configured bandwidth or its percentage. CBWFQ allows you to define what constitutes a class based on criteria that exceed the confines of flow. You need to maintain traffic classification on a per flow basis. Moreover, you can configure up to 64 discrete classes in a service policy. Now, let's talk about the drawback. So the only drawback of CBWFQ is that voice traffic can still suffer from unacceptable delays if CBWFQ is used as the only queuing mechanism. Now let's talk about low latency queuing or LLQ. Although WFQ provides a fair share of bandwidth to every flow and provides fair scheduling of its queues, it cannot provide guaranteed bandwidth and low delay to selected applications. For example, voice traffic may still compete with other aggressive flows in the WFQ queuing system because the WFQ system lacks priority scheduling for time-critical traffic classes. For CBWFQ, the weight for a packet belonging to a specific class is derived from the bandwidth that you assign to the class when you configured it. Therefore, the bandwidth assigned to the packets of a class determines the order in which packets are sent. All packets are serviced fairly based on this internal weight, and no class of packets may be granted strict priority. This scheme poses problems for voice traffic, which is largely intolerant of delay, especially variation in delay. For voice traffic, variations in delay introduce irregularities of transmission, heard as jitter in the conversation. LLQ reduces the jitter in voice conversations. They enqueue real-time traffic to a strict priority queue You configure the priority command for the class after you specify the name class within the policy map. Within the policy map, you can give one or more classes priority status. When multiple classes within a single policy map are configured as priority classes, all traffic from these classes is enqueued to the same single strict priority queue. LLQ extends CBWFQ by adding strict priority queuing. Strict priority queuing allows delay-sensitive data such as voice to be dequeued and sent first. Voice packets that enter the LLQ system are sent to the priority queue part of the LLQ system, where they have a fixed bandwidth allocation and where they are served first. Data packets enter the CBWFQ system directly, where they are treated accordingly to the CBWFQ assigned weights. Without LLQ, CBWFQ provides weighted queuing based on defined per class bandwidth with no strict priority queue available for real-time traffic. CBWFQ allows you to define traffic classes and then assign characteristics to that class. For example, you can designate the minimum bandwidth delivered to the class during congestion. One of the benefits of LLQ is having a consistent configuration across all media types, irrespective of the media used. Also, with LLQ, the entrance criteria for a class can be as granular as you like because you define it by an ACL. You are not limited, as with the IP RTP priority feature, to a simple UDP port range. If the port range feature had not been changed, it is probable that every future voice application would take advantage of it, knowing that the application would be preferential treatment within the Cisco infrastructure. TCP supports traffic management mechanisms such as slow start and fast retransmit. When congestion occurs, TCP traffic tail drop can cause TCP global synchronization, resulting in poor bandwidth use. This lesson will explain how TCP, in conjunction with random early detection, weighted RED and class-based WRED, manages the traffic flow between two hosts, and it will then explain the effect of tail drop on the TCP traffic. So, when an interface on a router cannot transmit a packet immediately, the packet is queued, right? Either in an interface transmit ring or TX ring, or the interface output hold queue, depending on the switching path that is used. Packets are then taken out of the queue and eventually transmitted on the interface. If the arrival rate of packets to the output interface exceeds the ability of the router to buffer and forward traffic, the queues increase to their maximum length and the interface becomes congested. Tail drop is the default queuing response to congestion. Tail drop treats all traffic equally and does not differentiate among classes of service. Application may suffer performance degradation stemming from packet loss caused by tail drop. When the output queue is full and tail drop is in effect, all packets trying to enter the queue are dropped until the queue is no longer full. Weighted fair queuing, or WFQ, if configured on an interface, provides a more sophisticated scheme for dropping packet. WFQ punishes the most aggressive flows using a congestive discard threshold, or CDT, based dropping algorithm. The simple tail drop scheme does not work well in environments with large number of TCP flows or in environment in which selective dropping is required. Understanding the network interaction between the TCP stack intelligence and dropping is required to implement a more efficient and fair dropping scheme. Especially in service provider environments, tail drop has the following shortcomings. Normally, when congestion occurs, dropping affects most of the TCP sessions, which simultaneously back off and then restart again. This process causes inefficient link utilization at the congestion point. To avoid dropping of TCP packets, TCP reduces the window size. TCP starvation. TCP starvation occurs in which all buffers are temporarily seized by aggressive flows, and normal TCP flows experience buffer starvation. No differentiated drop. There's no differentiated drop mechanism, and therefore higher priority traffic is dropped in the same way as best effort traffic. TCP synchronization. If the receiving router drops all traffic that exceeds the queue limit, as is done by default, many TCP sessions then simultaneously go into slow start. Traffic temporarily slows down to the extreme, and then all flows go into slow start again. This activity creates a condition called global synchronization. Global synchronization occurs as waves of congestion crest, only to be followed by throws during the transmission link is not fully used. Global synchronization of TCP host can occur because packets are dropped all at once. Global synchronization occurs when multiple TCP hosts reduce their transmission rates in response to packet dropping. When congestion is reduced, their transmission rates are increased. The waves of transmission known as global synchronization result in significant link underutilization. During periods of congestion, packets are queued up to the full queue length, which may cause increased delay for packets already in the queue. In addition, queuing introduces unequal delays for packets of the same flow, resulting in jitter. Another TCP-related phenomenon that reduces optimal throughput of network application is TCP starvation. When multiple flows are being transmitted through a router, some of these flows may be much more aggressive than the others. For instance, when the TCP transmit window increases for file transfer application, the TCP session can send a number of large packets to its destination. These packets immediately fill the queue on the router, and other less aggressive flows can be starved because there is no differentiated treatment indicating which packet should be dropped. As a result, less aggressive flows are dropped at the output interface. Tail drop is not the optimal mechanism for congestion avoidance and therefore should not be used. Instead, more intelligent congestion avoidance mechanisms should be used that are capable of slowing traffic before the congestion occurs. Let's talk about random early detection or RED. RED is a dropping mechanism that randomly drops packets before a queue is full. The dropping strategy is based primarily on the average queue length. That is, when the average size of the queue increases, RED is more likely to drop an incoming packet than when the average queue length is shorter. Because RED drops packets randomly, it has no per-flow intelligence. The rationale is that an aggressive flow will represent most of the arriving traffic, and it is likely that RED will drop a packet of an aggressive session. RED, therefore, punishes more aggressive sessions with a higher statistical probability and is able to somewhat selectively slow the most significant cause of congestion. Directing one TCP session at a time to slow down the flows for full utilization of the bandwidth rather than utilization that manifests itself as crest and throws of traffic. As a result of implementing RED, TCP global synchronization is much less likely to occur, and TCP can utilize link bandwidth more efficiently. In RED implementations, the average queue size also decreased significantly, because the possibility of the queue filling up is reduced. This is because of very aggressive dropping in the event of traffic bursts when the queue is already quite full. RED distributes losses over time and normally maintains a low queue depth while absorbing traffic spikes. RED can also utilize IP precedence or DSCP bits in packets to establish different drop profiles for different classes of traffic. RED is useful only when the bulk of the traffic is TCP traffic. With TCP, drop packets indicate congestion, so the packet source reduces its transmission rate. With other protocols, packet sources might not respond or might resend drop packets at the same rate, and so dropping packets might not decrease congestion. What are the RED modes? Based on the average queue size, RED has three dropping modes. Number one is when the average queue size is between 0 and the configured minimum threshold, no drops occur and all packets are queued. The second is when the average queue size is between the configured minimum threshold and the configured maximum threshold. At this point, random drops occur, which is linearly proportional to the mark probability denominator and the average queue length. The third one is when the average queue size is at or higher than the maximum threshold. WRED performs full drop in the queue. This situation is unlikely because WRED should slow down TCP traffic ahead of congestion. If a lot of non-TCP traffic is present, WRED cannot effectively drop traffic to reduce congestion, and tail drops are likely to occur. Now let's talk about WRED. Weighted Random Early Detection, or WRED, combines RED or RED with IP precedence or DSCP and performs packet dropping based on IP precedence or DSCP markings. As with RED, WRED monitors the average queue length in the router and determines when to begin discarding packets based on the length of the interface queue. When the average queue length exceeds the user-specified minimum threshold, WRED begins to randomly drop packets with a certain probability. If the average length of the queue continues to increase so that it becomes larger than the user-specified maximum threshold, WRED reverts to a tail drop packet discard strategy, in which all incoming packets are dropped. The idea behind using WRED is to maintain the queue length at the level somewhere below the maximum threshold and to implement different drop policies for different classes of traffic. WRED can selectively discard lower priority traffic when the interface becomes congested and can provide differentiated performance characteristics for different classes of service. WRED can also be configured to produce non-weighted RED behavior. The CBWFQ or class-based weighted for queuing system supports the use of WRED inside the queuing system, thereby implementing class-based WRED. Each class is queued in its separate queue and has a queue limit, performing tail drop by default. WRED can be configured as the preferred dropping method in a queue, implementing a differentiated drop based on traffic class and further on the IP precedence or DSCP value. The combination of CBWFQ and WRED on a single device is currently the only way to implement the DiffServ assured forwarding per hop behavior using Cisco software. Now let's talk about traffic policing and shaping. Both traffic shaping and policing mechanisms are traffic conditioning mechanisms that are used in a network to control the traffic rate. Both mechanisms use classification so that they can differentiate traffic. They both measure the rate of the traffic and compare that rate to the configured traffic shaping or traffic policing policy. The difference between the traffic shaping and policing can be described in terms of their implementation. Traffic policing drops excess traffic to control traffic flow within specified rate limits. Traffic policing does not introduce any delay to traffic that conforms to traffic policies. Traffic policing can cause more TCP retransmissions because traffic in excess of specified limits is being dropped. Traffic policing mechanisms such as class-based policing or CAR or committed access rate also have marking capabilities in addition to rate limiting capabilities. Instead of dropping the excess traffic, traffic policing can mark and then send the excess traffic. This feature allows the excess traffic to be remarked with a lower priority before the excess traffic is sent out. So what is traffic shaping? Traffic shaping buffers excessive traffic so that the traffic stays within the desired state. With traffic shaping, traffic bursts are smoothed out by queuing the excess traffic to produce a steadier flow of data. Reducing traffic bursts helps reduce congestion in the network. Traffic shapers such as class-based shaping, virtual IP-based distributed traffic shaping or DTS, and Cisco software do not have the ability to mark traffic. So how do we differentiate policing versus shaping? So policing can be applied to either the inbound or outbound direction, while shaping can be applied only in the outbound direction. Policing drops non-conforming traffic instead of queuing the traffic like shaping. Policing also supports marking the traffic. Traffic policing is more efficient in terms of memory utilization than traffic shaping because no additional queuing of packets is needed. Both traffic policing and shaping ensure the traffic does not exceed a bandwidth limit, but each mechanism has different impacts on the traffic. Policing drops packets more often, generally causing more retransmission of connection-oriented protocols such as TCP. Shaping adds variable delay to traffic, possibly causing jitter. Shaping queues excess traffic by holding packets in a shaping queue. Traffic shaping is used to shape the outbound traffic flow when the outbound traffic rate is higher than the configured rate. Traffic shaping smoothens traffic by storing traffic above the configured rate in a shaping queue. Therefore, shaping increases buffer utilization on a router and causes unpredictable packet delays. Interactive traffic such as Telnet and VoIP is susceptible to increased latency when network processes using large packets such as bulk FTP traverse WAN links. Packet delays is especially significant when FTP packets are queued on slower links within the WAN. To solve delay problems on slow links, a method of fragmenting larger frames and then queuing the smaller frames between fragments of the larger frames is required. To meet this requirement, tools such as header and payload compression and link fragmentation and interleaving can be used to reduce the size of frames that are sent on the WAN links. There are also some link-specific tools that we can use. We can use the shaping tool. So a shaper typically delays excessive traffic above an administratively defined rate using a buffer to hold packets and shape the flow when the data rate of the source is higher than expected. Link fragmentation and interleaving tools. With slow speed WAN circuits, a large data packet takes an excessively long time to be placed onto the wire. This delay, called serialization delay, can easily cause a VoIP packet to exceed its delay and/or jitter threshold. There are also some compression tools like compression techniques such as compressed RTP or CRTP real-time protocol. It minimizes the bandwidth requirements and are highly useful on slow links. At 40 bytes total, the header portion of a VoIP packet is relatively large and can account for nearly 2/3 of the entire VoIP packet. To avoid the unnecessary consumption of available bandwidth, you can use compressed RTP or CRTP on a link-by-link basis. CRTP compresses IP, UDP, and RTP headers from 40 bytes to between 2 and 5 bytes, which results in a bandwidth savings of approximately 66% for G.729 VoIP. And the last one is the transmit ring, or what we call as the TX ring tuning. The TX ring is a final interface first in, first out queue that holds frames to be immediately transmitted by the physical interface. The TX ring ensures that a frame is always available when the interface is ready to transmit traffic, so that link utilization is driven to 100% of the capacity. The size of the TX ring is dependent on the hardware, software, and layer 2 media and queuing algorithm configured on the interface. The TX ring may have to be tuned on a certain platform interfaces to prevent unnecessary delay jitter introduced by this final FIFO queue. In this lesson, you have learned about what a QoS is, what are the QoS model, and what are the QoS toolsets. So this QoS toolsets, we spoke about classification and marking, congestion management, congestion avoidance, traffic policing and shaping, and the link-specific tools. Thank you.